Okay, thank you for the wonderful presentations. All the presentations are great. Also, thank you, Chunjung, for playing the videos. And now we have about half an hour for discussions. We have 9 papers. We have half an hour. So if we have some general questions, that would be better. If not, we can also take some specific questions, probably one specific question for each paper. Then I also prepared some general questions because this is supposed to be a panel discussion. Okay, Evan, help us select some paper, some questions. This question is for M-Sense. Radar reflections depend on distance as well as radar cross-section. How do you address the robustness against distance and the size of material?
Hello, thank you for the question. So in our application, it's a mobile scenario. So we imagine the user will hold the radar and move towards the target. So in that case, our system actually works for different sizes, for objects with different sizes. Because as long as we can get reflection from any surface of that target, we will get the response. And from that, we can estimate the material feature. So it doesn't really matter, although it depends on distance. And of course, we didn't test against very large distance because we don't think that would be the practical application scenario. You don't usually to scan the materials for targets far away. So we are more focused on objects that are close by. Hope that answers the question.
Another question which is close or relevant, does the shape of the object affect the result? For example, also, if we have a plastic object placed on a metallic surface, what will be the result?
So since we are using the reflection signals only, as we also admitted in the paper, we only sense the material of the surface material. We cannot sense through inside the target. So if plastic is on the surface, then we will sense it as plastic. And the shape, as long as it is a relatively flat surface, it should be fine. But we also tested with some slightly curved and non-flat objects in our paper. You can refer for more details. But if it is, for example, a purely curved surface, then I think we will have problem because due to the specular refraction, we might not be able to get the reflection signals from that surface. Yeah.
Okay, thank you. Next question, go to the RFID tattoo paper. Yeah. For training machine learning, deep learning models, are the training processes performed individually, person-wise? Did your project find difficulties in this regard? If it did, what were your results?
Yes, thanks for the question. So in our paper, we didn't perform like individual training process for individual users. We trained the data set across a bunch of users. And also in our paper, we evaluated the cases that where the per user is not performed. And also we have a pre-calibration process when the user is used before the user is used our system. So basically we can ensure that different users, because different users have different skin electrical property, and we eliminated this influence by using this collaboration process. Yeah.
Okay, thank you. Next question for white border paper. Does the activity detection module generalize to multiple subjects?
Thanks for the question. So for Y-bonder, if the two people take activities in two different areas, and our system can detect there is a human motion in these two areas. But if the two people get into one area, and it's very difficult for our system to differentiate this signal is from the which person. So so far our system could know the in which area the human is taking the motion, and two person in the two different areas we can know that, but they get into the same area, we can detect that. Yes.
Okay, thank you. I have two kids around me, so it's kind of challenging. Okay, the next question is for the multi-sense Wi-Fi paper. Thanks for Light's presentation. What I am curious about is whether the upper limb motion has a big impact on detection performance. This is for the multi-sense Wi-Fi paper. Let me repeat this question. I'm curious whether the upper limb motion has a big impact on detection performance.
Up motion.
Like the upper, your hands, arms, will that have a big impact compared to the rest of your body? I think that's probably what they're asking.
Okay, thank you. So actually the up motion really has a significant effect on the multi-sense system. Yes.
Okay, it has a significant impact.
Yes.
Okay.
So basically, the system works actually when when the people is not moving. So only people are in still. Actually, only people are still in the still mode. Actually, we can measure the respiration rate. Yeah.
Okay. Thank you, Dachin, for clarification. Next question is for V2I5. Would in-car multipass response confuse user assignment as it introduces residual fast time peaks?
Could you please repeat the question?
Okay. Would in-car multipass response confuse user assignment as it introduces residual fast time peaks?
Yes. So according to our experiment, the line of sight signals dominate the multipath signals. So the multipath signals can actually be neglected, while the signals reflected directly from the users dominates. So it is not a serious problem.
Okay. So there's one more question for you as well. How does the vibration decomposition work under different road conditions and driving speed? And how do you handle hand and body motions?
Yes, so the vibration from the car and also the motion from the vehicle are actually treated as noise. So if there are too much noise, we just, in one page of my presentation, we just discard the frames and we output nothing. And if the noise is under the desired level, we output the vital sign, the respiration frequency, heartbeat signals.
Okay, yeah, I remember that slide. You mentioned the road conditions. You'll also do that when you have body and hand motions, right? Just
right,
discard
that's
it for
right.
now. Okay. Okay, I think those are the specific questions I received. Now there are some general questions. I think general questions always probably more intriguing for a panel. This is a quite big question, probably. Okay, what do you think, this is asked by Koji, what do you think the grand challenges for us are in the next 5 to 10 years? For example, more accurate sensing, theoretical models, new application. For example, something only RF sensing can do. What's a big challenge?
I think let me try and answer that. One of the big challenges would be accurate through-wall imaging, as well as accurate body sensing, understanding what's happening inside the body very accurately. Because one of the challenges with, I mean, if you go to the doctor and you're getting an X-ray, ultrasound, any of these done, it's so much more challenging than, let's say, having your smartwatch or your cell phone being able to do it automatically on the fly. So I think a lot of the talks today have touched upon different aspects of health and body sensing, but if we can truly make it work in any environment as people walk and move, as well as target other domains like helping persons with disabilities as well in these contexts, that would be amazing.
Any
So
other
maybe,
panelist?
yeah, maybe. Can you hear me, Grant?
Yes, let's go ahead.
Hi. So yeah, just speaking about the grand challenge for the next 5 to 10 years. I imagine the question by Koji refers to the grand challenge for our community. And I think, of course, there are many applications where a community that really thrives on identifying applications in other domains to work on. But I think one of the challenges for us will be to figure out what is our role in working with other application domains. So for example, health is a big area, transport as well, et cetera, et cetera. What is our role? How do we approach collaboration with, say, health experts? Are we seen as programmers? Are we experts on something? There's this expression, jack of many trades, master of none. So our community seems to be doing all kinds of sensing for all kinds of applications, but I'm not sure we're getting through to other communities, and we're not really planting a flag on an area and saying, this is our thing. And I contrast our community to biomedical engineering, which has a very well-defined scope. They have a kind of established relationships with the health industry, I should say, health researchers, and an established set of tools and so on. So I guess what I would say is that we're still trying to develop our identity as scientists, and we're trying to develop a coherent story to tell about what is our expertise, what we can offer, what are the kinds of problems that we're good at solving.
Very good.
I'd like to add a little bit to Veselis. Hope I pronounced your name correctly. Yeah, more from the kind of the industrial perspective. Since I'm not only with the University of Maryland, but also with the Origin Wireless, a startup on commercializing wireless sensing. So I guess one big challenge is that we are seeing tons of papers on RF sensing as like this section show. But how do we really make them real products? I cannot share too much, but one example is that it took us a team for like more than 2 years to commercialize a simple motion detection product, which we are happy to show that that's already in market right now, but it's a long way. And that will be more difficult if we want to commercialize like sleep monitoring for detection. There are many things actually beyond what we can imagine, purely inside the research and academia community. So I think we need to really, for the next 5 to 10 years, I think some researchers need to step out of the pure research and think about how we really make those become real products and benefits more people. That's one thing. And back to the research side, I think one challenge I see is how can we really handle multiple user sensing in practice. That's always treated as a big challenge if we are using low frequency bandwidth signal. Sorry, last thing is the echo back to Vasilis, is that, for example, we are doing a lot of breathing and vital sign monitoring. And we have, of course, we have some sort of ground truth measured, and we compare, okay, we report high accuracy. But how do we really validate this kind of data are valid and medical meaningful with collaborations with medical professionals? We are carrying out some efforts here, but the gap is a little bit, the bar is a little bit high actually when we are touching with the so-called medical or healthcare industry. They have their kind of gold standard, and they are it's just not that easy to convince them, okay, what we sense makes sense. Yeah. Thank you.
Okay. Actually, I want to follow
small
on.
thing to add it, one is, this is Parth, sorry. So yeah, I think I wanted to add something that what Changshu said and Vasilis and Solon said as well. I think one thing that specific to RF sensing is that we have one directions where we are actually creating newer and newer applications that we can solve with RF sensing. But when we actually make these products, take the step from going from research to a product, robustness becomes a very important problem. And I think at some point we'll have to take a step back and think about how to make these things robust in order for them to be more useful, as opposed to, of course, making new applications, new things to do with RF sensing is an exciting direction, and I'm myself very interested in that. But going from research to commercialization to some extent requires addressing the robustness issue, how robust it is compared to other modes of.
Yeah, RF sensing, like for this session, I think we are very unique in that we're contactless. I mean, UbiComp computing, we have been talking about activity recognition for a long time, but with different generation of sensors. Some are very intrusive, bulky. Then later it's less intrusive, but it's still wearable, so you have to wear it. But for RF, you don't need to wear it. Think about the Wi-Fi coverage. If all the Wi-Fi coverage can be utilized to classify all kinds of activities without wearing an RF receiver, we can throw away all the smartwatches, smartphones, Fitbit. We can still get its functions. So I think that part is quite unique. And the deployment of the wireless coverage, you talk about, depending on which radio you're using for sensing, right? Wi-Fi, RFID, 4G, 5G in the low route talking about today. They're already there. If it can be commercialized, I think that's a big and unique opportunity.
I agree. And so kind of one thing has been our desire to aim for non-invasive sensing. Another one has been our eagerness to turn noise into data. Gregory about articulated that. And I think another perhaps an unwritten objective, which comes a bit from our kind of link to human-computer interaction and our interest in users and user-centered, is that a lot of the sensing we do is sensing of people's behavior. And that's a bit tricky one because I guess it lends itself to applications very well. But when it comes to behavior, you know, that it's kind of at the intersection of multiple disciplines by default. So of course you have psychology and sociology, but then you have perhaps more on the medical side. So in a way, we're kind of interested in sensing something, behavior, which is by itself at the intersection of lots of disciplines. Yeah.
I think just to add one more thing to our session chair, I think another unique advantage for RF sensing, especially Wi-Fi sensing, is that it's really, really low cost. It reused existing hardware, and it's not only non-contact, it's just very low cost. So eventually what kind of signal will be used will be decided basically by the market and by the industry. But cost, most of the time, is their first factor to consider. So again, taking our motion detection, we translate it as a motion security application. So it's really easy to be accepted just because users don't need to purchase a new hardware. It just is some software on top of their home router, which is already inside their home. And more broadly, so Wi-Fi is essential to all the IoT devices, I guess. And imagine like billions of IoT devices, even you add a dedicated sensor, which is like cost 5 cents, it is 5 cents. When times billions of devices, that would be a lot. So I think that's another unique advantage of Wi-Fi sensing.
Yeah, actually, to add one point is like, actually we should also think about the limitations of different wireless technologies. Basically, we need to really develop the theory to understand, what kind of limitations, what kind of limits we can sense with different, kind of wireless signals. Actually, in this regard, my team in Peking University, we are trying to develop the theory, actually to understand the sensing, bound of different kind of wireless signals, and so that in the future we could design maybe specific devices which you can make, the sensing in different conditions possible. For example, if you want to sense, for example, human respiration and what kind of signal is the best. And if you want to sense, for example, fall down, what kind of signals are the best choices? So basically, those things need to be considered in different, different ways. Of course, we can leverage on the commodity devices to do certain kind of sensing, but that not guarantee us to sense any kind of activities. So basically, we need to think both ways. Yeah.
So talking about limitations, I would also add like security and privacy is one of the big challenges, because if we go with the vision of, hey, your Wi-Fi access point also sensing your breathing, your every move, that leaves a lot of people uncomfortable. So how do you create a privacy framework around this sort of a solution where you have to add tin foils all around you all the time? Or is there a mechanism for user consent to also play a role in this system? Or is there a way in which we can do wireless sensing, but more limited to around the user's body? So we've also been looking at privacy aspects of systems as well. We in our lab have focused more on body sensing for this reason. We're worried about that alternate future, but it's going to come anyway. And it's if anybody's going to address this question, it's going to be us as a community.
Okay, wonderful. To follow up the point from Daqing, I think theory is very, very important. If we look at the papers in this session, we have application, right? We have hardware. Together with the hardware, we have signal processing technique. Then we have modeling, from traditional machine learning to neural network, right? So we also have user static. But if you look at this theory, I think probably we need new, like if you talk about, depending on radio, which frequency range, how long, material, even like the networking and the communication community have a lot of theories on how to use the radio to communicate, right? We probably should have theory on how radio should be used for sensing as well, to expand the digital signal processing. Even for the machine learning right now, I think one big challenge I have been facing is that if we really want our community, this kind of sensing to really take off, you cannot ask your customers to collect the data for you to train, right? You have to do something that after you ship your solution to your customer, you don't expect to collect anything from there. Your machine learning model, whatever model, should be really leave one subject out and very robust. How to deal with that? I think it's a very big challenge, no matter which RF sensing you're using right now, which application you're using. Also, when it comes to the healthcare community, I happen to work a lot with healthcare communities. Their applications are killer applications. All of them are killer applications. People are willing to pay for that. But in order to get a solution, you wanted to scale up from one person solution to 1 million person solution without linearly increase your cost. So how to get models that can work on same people and the scenario is really one of the keys. Probably one small question to challenge panelists, which is still under the big umbrella of Koji, is that what if we scale your sensing on your paper to a city scale sensing? What's a new challenge?
I think it varies for different papers. In our paper is an on-body system, so I think it's going to be relatively easy to scale if everyone has it, right? But I think answering your question more broadly about is there a way to deploy cellular like infrastructure everywhere and then sense everything that's happening around us, if that's the vein of your question, I think the biggest challenge is going to be multipath, the sheer amount of different things going on in a city scale environment that's going to be extremely hard to sense and disentangle without having a large number of gateways and devices that really defeats the purpose. But I think if you're thinking about maybe sensing large scale events, let's say an earthquake or a disaster, maybe if the event that you're sensing is also large scale, perhaps there's a direction there that maybe that's the right place to start, if you ask me. But could your cell towers without a device on you know that you are there like 10 miles away using pure RF? I would doubt it if I see it, but I'm curious.
Even for the RFID tattoo, like you sense individuals, but the models, I think when the models from 1 million individuals get combined together and under the startup of Sararan, Google, something like that, your modeling probably will benefit by looking at all the individuals together. Yes,
but I'm scared of that future. But yes, you're right. Absolutely. All of these models are our approaches, right? I think this point was mentioned earlier as well, right? Commercialization, there's this big step of commercialization that a lot of these technologies need to take. I applaud those who have already taken the plunge. And once you get there, right? Imagine how Alexa has improved over the years, just because, or Siri has improved over the years just because of the amount of data collected, or image classification, for example. So the same phenomenon could happen to RF sensing as well. Now there are pros and cons there. At least it's not, I would say at least it's not images. Images are already, our video data is perhaps more privacy intrusive than RF in some instances. But I think the same being privacy, not worrying about privacy for a moment, the same phenomenon can of course very much apply to RF too. I agree with that.
Yeah, on the other hand, actually, we are trying to, find ways, maybe to reduce the training, or maybe just avoid the training in some, in certain ways. In this way, we, for example, we develop different kind of algorithms so that we don't need to do any training. In this way, our method can be applied to different kind of contexts. Without being trained. So basically, this is of course in the end, after we get very good algorithms, probably we can also introduce for example, deep learning or this kind of data intensive method to to help the approach. So I think maybe this is maybe one possibility to to make the system, wireless systems applicable to different conditions and also at a large scale. Yeah.
I want to add to what just Professor Zhou and Professor Zhang just said, is that the data collection and domain adaptation of RF sensing is very important. So one of the solution is to employ meta learning and transfer learning and combine it with RF sensing to solve the problem. And I think if you are interested, you can look at our recent census paper, and we have a great detail about domain adaptation and how to solve the data scarcity problem.
So maybe just a quick reflection on my part. The question is, imagine if your system was scaled up to a city or a country. And I want to very quickly reverse engineer that. So if that's how things are in 20, 30 years, just judging by how things happen today, if sensing is everywhere, I would assume that's probably 2 or 3 big players who are controlling that sensing, right? And have the capability to make it happen. And what we know that although we as researchers have very noble objectives in our work, and we can always point out, the noble applications, that's not always the case with industry that is looking to make profits. So a big issue would be around things like who owns the data, who can access the data, and what are those organizations doing with this data? So for example, very soon, I think, self-driving cars and LiDAR, they're collecting a lot of data that's already being analyzed through crowdsourcing, etc. What's going to be happening with that data? Could the government get access to this data to enact noble applications or not? So unfortunately, all these issues are coming up, and increasingly there is this notion that although the previous century was very much shaped by people in finance and bankers and those kinds of people who made decisions that impacted lots of lives, this century is very likely to be impacted by technologists. And it's interesting to think about how we think about the world and how we think the world should be, and what effect is that going to have on billions of people over the next few decades.
Okay.
Yeah, I want to add on the point about city-scale sensing or city-scale communication. And nowadays we are thinking about like deployed trillions of IoT devices across cities, across countries. And you can imagine is that trillions of batteries on the small client like LoRa device. And frustrating challenge is that we need to do maintenance to replace the battery, because the battery cannot last for long. So one possible direction is that how can we achieve a battery-free solution that we don't need to change the battery for every single client that deployed in our city. And if we can deploy this kind of wireless technology, I think we can also have put a step towards city-scale sensing or city-scale communication.
Thank you. I think we're running out of time. We had a wonderful discussion. I think asked more questions than we answered, which is good. So we all have questions to work on and come back next year with great papers.